this also tells you a main assumption about Poisson processes. So there's no evidence that Boeing believed the emission was tied to the battery's age. So that is because, so Boeing doesn't give access to their data, so you don't have access to their data. But this is because 10 million flight hours would be amassed by many different 787s at different ages, which means that data for the newest batteries is combined with data for the oldest batteries. So what we're seeing in these flight hours is some batteries are young, some batteries are old. All we're seeing is every once in a while we get an emission. And what this leads you to do is you're trying to think about how these emissions happen. And before I do this next sentence, let me just graphically think about how am I thinking about these emissions. So you're sitting there and you're watching for smoke emissions. And this is time. So this is time. And so you're sitting here at 0 and you're saying, okay, when is the first smoke emission? Well, I don't know, maybe it happens after 500,000 hours. So that's the event. This is an event. The first event here is a smoke emission at, let's say, 500,000 hours. And maybe you wait a little bit more and the next one happens at sort of 2 million hours. So this is what you're imagining. You're tracking, these planes are flying, time is going on, time is passing, and you're tracking, when do I get a smoke emission? After how many flying hours? Now, where does this Poisson process come up? So, I said something about all these batteries of different ages, youngest, oldest, they're all mixed together, so there's no reason to believe that it's more likely that a battery is going to fail here than it's going to, fail, that I'm going to have a smoke emission here than I'm going to have it here. So what we're assuming that's making this a Poisson process is there's an assumption that if I look at some interval of time here, and I want to know about the probability of whether or not I'm going to have an emission. So this is the probability of an emission between, I don't know, 600,000 hours and 600,000 hours in 1 minute, okay? So what matters for me is the size of this interval. So this delta I have in the slides is the delta is 1 minute. And I'm saying that the probability of one emission should be approximately equal to the length of the interval. So that's what I'm calling this delta. That's like this 1 minute. It should be equal to the length of the interval times the rate at which emissions are occurring. And my main hypothesis here for this Poisson process is it doesn't matter if I'm looking here or closer to 0 or way out there. My probability that I'm going to see one of these emissions is basically proportional to the length of that interval. Okay, so that's what I'm saying right here. This leads Trojan consultants to decide that a reasonable model is to assume that at any small interval of time, the probability of seeing one smoke emission is approximately delta times lambda. And what's lambda? Well, lambda is the rate at which emissions are occurring. And furthermore, the probability of seeing 0 smoke emissions, so the probability of 0 emissions, should be close to 1 minus delta times the rate at which these emissions are occurring. And the probability of more is close to 0. So that seems sort of reasonable, because it seems like if I look at a very small interval time, I'm going to get 0 emission or 1 emission. I'm not going to get 5, I'm not going to get 2, I'm not going to get 3. Okay? So that's our main hypothesis. Now, what is the rate that these emissions are occurring? So you tell me, what is Boeing telling us? Boeing is telling us the rate at which these emissions are occurring, and what does Boeing say?
Once every 10, or less than once every 10 million flight hours?
Yeah, and I'm even going to give you, the benefit of the doubt, and I'll say once in every 10 million. So let me use the lower bound on that, right? So this rate that emissions are occurring is emissions are occurring at rate 1 over 12 million. 10 million, sorry. 10 million. first question, which is what should be the rate that, what should be this rate lambda using Boeing's estimation. Now, what am I going to do with that? If I want Deborah to go back with some hard facts, and she's sitting here thinking about whether or not she's going to tell Boeing that they're kind of blowing smoke, she needs a reason, a more quantitative reason to say that. And so what she really wants to know is what's the probability that this second smoke emission would occur before the 100,000th flight hour, assuming that we have this Poisson process, okay? So she's asked Trojan Consultants, we've said this is this is a reasonable model to be working with. And what we need to tell her is what's the probability that that second smoke emission would occur before the 1,000th flight hour? Because that's what she's seen. Is that not consistent with what Boeing is telling us? So let's say I give you a random variable that is the time until the second emission. What distribution should that random variable be? Gamma, right? What's the distribution of time until the first event in a Poisson process? It's exponential. So the time until you see that first emission is exponential. The time until you see that second emission is again exponential. I'm summing two exponentials, so I have a gamma. So whenever I say Poisson process and I want time until nth event, I got a gamma distribution. So what we are interested here is we are interested in a random variable x. The random variable x represents the time until the second emission, assuming Boeing's arrival rate estimate, and their arrival rate that I've been calling lambda, is equal to this 1/10 million, right? And we're saying this x has a gamma distribution. And there are two parameters in this gamma. The one parameter is the n equals 2, because we're looking at the second smoke emission, so the second event occurrence in this Poisson process. And the other parameter you need is this lambda. It's the mean, it's the rate at which events are occurring, or it's the mean time until an event occurs, whichever way you want to look at it. So what's the probability calculation that is relevant to Deborah? Is it whether or not x is less than 10? What if I tell you that, actually, in this model, the probability of seeing two smoke emissions in 100,000 hours is like 10%? Would that be an interesting fact? Okay, so what I want to know is, we have seen two smoke emissions in 100,000 hours. Boeing is telling me that you're only getting one smoke emission every 10 million hours, and I'm thinking that's suspicious. So what I want to know is if I use Boeing's own estimate of this one smoke emission every 10 million hours, what is the probability that I see two in 100,000 hours?
There shouldn't, like they say there's only one in 10 million, then there shouldn't be two in 100,000.
One would think. But we know it's random, right? If Boeing says it's 1 in 10 million, and I tell you that, well, the first emission occurred after 8 million hours, would you raise an eyebrow? Yeah.
It's still close.
It's still close, yeah. So the question is, what is close? Right? So I want to quantify close. So this is why Deborah's raised her eyebrow. Deborah's raised her eyebrow for exactly what you mentioned, which is they told me 10 million, and it's not even 1 in 100,000, it's 2 in 100,000. This is really suspicious. And I want to put a hard number on what is the probability that we will actually be getting 2 in 100,000. And if I say that that's basically infinitesimally small, that would support her estimate, and she can go back to Boeing and say, yeah, you need to work on you're doing something wrong. So we want to know what is the probability that x, the time until this second emission, is occurring for 100,000 flying hours. Would you agree with that? Okay, and so last time when we did this, I said gamma was sum of two exponentials. You can use a simulation. You can simulate each of these exponentials. We've sort of seen how to do this with this inverse transform method. I didn't actually say that you could also use a gamma.dist function in Excel, so let's do that so that we don't have to do the simulation. So in this case, we don't need the simulation. This is a gamma distribution, and so it's gamma.dist, and the first parameter, it's exactly like gamma.dist, but I'm asking it for a different distribution. So the first parameter is 100,000, because I want to know the probability that x is less than or equal to 100,000. The second parameter here is the 2, because I'm summing two exponentials. I'm waiting for the second event occurrence. The third parameter is the mean time between event occurrences. So the third parameter is the mean time until, in this example, I see a smoke emission, which is 10 million flying hours. So that's 10 million. And the last parameter is toggled on 1 or 0, depending on if you want the probability, the CDF, or the PDF. So that's the same idea as the normal there. And now somebody can make that calculation for me.
.00497%.
Yeah, and if 0.00497%, so I'd actually need to add two more zeros, because say it's like 10 to the negative fifth.
Yeah.
So it should be like 4.97 times 10 to the negative fifth. And to respond to your question that, yeah, no, that's just 100,000 is too little if they told me 10 million. Yes, I agree with you, it's too little. And now we have, how exactly too little is it? Well, this says it's only sort of on the order of 10 to the negative fifth probability that I would see that, right? So that's pretty small. I would call that basically 0. So that gives Deborah like some pretty hard quantitative pushback that's like, I just don't believe this 1 in 10 million that you're estimating can be right, and you're probably not ready to fly. Is that good?
You have to explain the alpha and beta.
Yes. So I think Excel is calling it alpha and beta. So one thing I didn't say is gamma distribution is actually more general than when I'm just saying exponentials. So when you look at your Excel, alpha doesn't necessarily have to be an integer. And the way we've been thinking about it, that first argument is always an integer because I'm thinking of summing exponentials, and this is the number I'm summing. And so for me, I'm waiting until the second event occurrence. The time until first event is 1 exponential. The time from first event to second event is another exponential, and that gives me 2 exponentials that I'm summing, and that's why that alpha is 2. And the other parameter, the beta, is related to this arrival rate. So Excel is asking it not for the rate, but for the time until the first smoke emission, or the time in between these two different emissions. Is that? And just as a word of warning, when you go into different software packages and you're looking at gammas and exponentials and Poisson processes, half the time, some of them will want it as the rate, some of them will want it as the time. So be aware that it's very, between different software packages, there's, as far as I can tell, no commonality. Sometimes they want it as the rate, i.e. the 1/10. Sometimes they want it like Excel as the time, like the 10.
And could you explain to me why we care about the 100 before the 100,000th flight hour?
Because that's what happened. So what happened was we saw this Boeing 787 have 2 smoke emissions before the 100,000th flight hour. Boeing is telling us that when they ran their own tests, this is only happening once in every 10 million hours. And the FAA, now here I don't understand enough to give you all the exact parameters. There's a new article that you can click on in the slides to see a little bit more. But we're basically saying to Boeing that we don't believe the tests you're doing. We don't believe your 1 in 10 million number, because what we saw is 1 in 100,000.
2 in 100,000.
Sorry, 2 in 100,000.
And so if the number that we came back with once we did that gamma dot dist function was higher, like significantly higher, then we would say we believe you?
Let's even say it was like 10%.
Okay.
If it was 10%, okay, maybe it's a little bit unlikely. Let's even say it was 1%. It's unlikely, but is it really unlikely enough that we're gonna push back at Boeing and say, we don't believe, we think you're lying to us, we think you conducted your tests incorrectly?
Okay.
So I'm really asking for is the number coming out of Boeing tests consistent with what I've seen, and I don't have access to what they're doing. I just know that something's fishy here. And before I'm gonna make a big congressional stink about it, I wanna make sure that, like, I'm really clear something's fishy here.
Okay.
That,
Definitely.
okay. Okay, so that was opening exercise 1, and that was just to sort of, a little bit more familiar with, if I say Poisson or exponential, you can really always think about it as events happening over time. Okay, and so there's a lot of times when it's nice to think about events happening over time. That was one example. One other example.
So from our calculations, there's 4.96 times 10 to the power 5 chance, like, or probability that this is likely, this would happen, right?
Yes,
So,
yes,
the conclusion is Boeing is lying,
yes,
right? Okay.
yes. Or they didn't conduct their test correctly or something, but we do not believe that what they are telling us, because they were saying if the once in 10 million flight hours is correct, then that's sufficient to certify you to fly.
Right.
And if we're gonna keep them grounded, then that means we're really saying that we don't believe that what you're telling us about this 1 in every 10 million flight hours is correct. Okay, so then I said most of this class is about sums, and I want to let you kind of do some sums for yourself. So I posted what I'll call it a little mini case. And you should have it that you can download it directly, but the idea here is that I'm thinking of is I'm doing some kind of new product launch. And I'm going to launch it in 2 cities simultaneously, LA and Beijing. And it's a new product, so I don't really have data on how many people are going to want it. So I'm going to say, I have no idea how much demand I'm going to have. I'll use a uniform distribution because that's sort of modeling my ignorance of having no idea if nobody's going to like it or a lot of people like it. I'll use a uniform, let's say 0, 1 million. So I have an idea of the absolute upper bound on my market. So I launched this product in LA and Beijing, same time, and I'm representing uniform random variable for my demand in LA and uniform for my demand in Beijing. But to the question of what is the boss interested in, the boss is interested in knowing the total demand distribution for this new product. And we'd rather it be higher than lower, obviously. And if we know the total demand distribution, we can start thinking about questions like how much inventory do we need to keep around of this product to make sure that when I launch the product and customers ask me for it, I can give it to them without having like so much inventory that it's sitting there and not very many people wanted the product. Okay, so the idea is it's somehow interesting to know what this total demand distribution is. Okay, and what I want you to know is we've done a lot on RAND and Uniform 01. We've done that out the wazoo. But now we're combining demand distributions. So what happens when I add LA demand to Beijing demand? That's my question to you. What's my demand distribution when I add LA and Beijing? Okay, so one way we could do this is, we don't know. I heard normal, I heard gamma, I heard, did I hear anything else? But the question is when I start combining things, I didn't hear uniform. So you seem to think that when I combine these two things, it's not going to be uniformly. Fair statement? Okay, so then the question is, what is it? And I posted a spreadsheet. Can you access the spreadsheet? It should say mini case and it should look something like this. My other class, we had some technical difficulties and they actually could not access it. But there should be a spreadsheet posted, minicase.xls. Okay. Okay, so I'm going to suggest that you figure this out for me. How can you figure it out for me? You can do some kind of simulation and you can say, well, in LA, that should be a rand, right? In Beijing, that should be a rand. If I want the sum of the demand, I can type that in column D. I can do a bunch of trials. I think I suggested you do 100. And then I can do a histogram plot, and that gives me an idea of what my demand distribution is. So I'm suggesting you do this is a Monte Carlo simulation for yourself to figure out what this unknown distribution is going to be. And let me give you, I don't know, 5 or 10 minutes to do it, and then we'll talk. So I think most people have their histograms, and there's several things I want to observe. But the first one is that this is not uniform. So the first one, consistent with what your guys' intuition was when we sum the demand, this is definitely not uniform. We started out with something where demand was equally likely to be anywhere between 0 and 1 million in both LA and Beijing. And when we summed them, that changed things. So that's the first thing. You know, we only did 100 trials, so there's not going to be a lot of consistency in these histograms. I expect that yours look different than mine, so... Oh, and I don't have the slides up, sorry. I suspect that yours look different than mine, so don't be worried if your histogram doesn't look exactly like it. But it definitely should not look uniform. So one thing that should be coming back is your histogram should definitely not look uniform. It should be suggesting, in fact, that you're getting more values around 1 than around 0 or 2. And just to explain that, what's the minimum and maximum values of demand that could be assumed here?
0
and 2. 0 if nobody likes it in both cities, 2 if everybody likes it in both cities. Not uniform. And most of you should be seeing a phenomenon where the values close to 1 seem a little bit more likely than the values close to 0 or 2. Why is that?
I was going to say the central limit theorem, but that's not true.
It's getting there though.
Well, for example, if the first one is high, like 1.5, the second one is low, then, I mean, like, yeah, the first one is high, the second one is low, and the second one is high, the second one. There's more chance that it's concentrated material.
So, Arkar, what you're observing is exactly it, right? If I get a 2, there's only one way I can get a 2.
Right.
1 and a 1.
Yep.
But if I want to get a 5, there's several different ways I can get a 5. Sorry, a 1. Several different ways I can get a 1. 0.5, 0.5, 0.75, 0.25, 0.6, 0.4. So somehow, the combinations close to the 1, there's just more combinations that make that happen. So it's not surprising that the values in the center are a little bit more likely than values at 0, 2. And that is definitely different than what we observe for either city individually. Okay? So that's the main observation I want coming out here.
Also, the expected value for each one is separately is 0.5, so you're expecting 0.5 plus 0.5 in general.
Okay, so this is a good question. I completely agree that I'm expecting 0.5 plus 0.5, which means the mean of the distribution should be 1. If I tell you the mean of the distribution is 1, does that say that I'm also assuming that values close to 0 are less likely than values close to 1?
No.
No. Yeah, so I completely agree with you, but, and I think this is a really good point, so that's why I'm kind of making it. Just because I know the mean is 1 does not mean that I know something about how that distribution shape looks like.
Should we expect the sum of two uniform distributions to be a normal distribution?
No,
No.
no,
So in
I
this
would not
case-
expect that.
In this case, it shouldn't tile off equally on both sides?
You know, we could do the calculation, it's a little bit algebraic, so we're not gonna do it. At this particular point, just observe that it's not uniform. And what you're saying, should it be normal? We're getting there. You and JP, the thought of central limit theorem and normal, we're getting there. So hold it till the second question. You're like 2 steps ahead, but we're getting there. Okay, so we've already said mean total demand should be 1. I'm summing across both of the cities. It's 0.5 and 0.5 for the mean separately. And remember, expected value is sum. So if I'm summing in random variables, the mean is the sum of the means. The variance, if you want to double check your simulation, I didn't tell you this, but uniform, I told you it several weeks ago. If I have a uniform random variable, the variance of a uniform is a 12th. So variance of uniform is a 12th. That means if I want to look at the variance of the sum, this is the variance of my combined demand, it's a 12th for LA plus a 12th for Beijing, so that's 2/12ths or a 6. And if I want the standard deviation of the total demand, I need to take the square root, so that should be 0.4. So if you take the standard deviation of your combined demand, you should be getting something close to 0.4. And I'm just kind of reminding you here that standard deviations don't add, variances add, and whenever you add variances, you're also making the assumption that you've got independence. And those 2 rands we're sampling completely independently from each other. Right now, we're assuming that Beijing and LA have completely independent demands. Of course, you may or may not like that assumption. So if you're launching a new product and you launch it in 2 different cities, maybe Beijing and LA have different cultures and they may react differently, but on the other hand, completely independent. Seems like you might want some dependence in there. So just to make a point, when you're doing these simulations, if you wanted dependence, how would you put in dependence? Did we have to do this as those demands being completely independent?
You can make LA dependent on what Beijing is. It's like a compromise.
when you look at column C, generate your RANs in column B, and in column C, do something like some function of column B. That would be a perfectly correlated demand. And you could get weaker or less weak correlations. So if in column C, you just typed exactly equal to B3, or any specific function of B3, you would be having perfect dependence there, because I tell you what LA demand is, you know exactly what Beijing demand is. You want something a little bit weaker, use a combination of what you're seeing in B3 and some kind of RAM. Okay? I would have to have some reason for what some function we're doing, but I just want to make the point that when you're using two separate RAMs in column B and column C, that's completely independent. If I want to make them partly dependent, make sure that C is doing something with B's RAND, or vice versa, B is doing something with C's RAND. Okay, so now it's your turn again. Let's go to what happens if we have 10 cities. Okay, so if we have 10 cities, I want to know what is the distribution of my total demand. So if you guys could do that for me.
Should we use the dependence or the independence?
Independence. Continue with independence. So what's the distribution of the total demand in 10 cities when everything's independent? down with something like this. And so what distribution do I have? Normal. Okay, so you've just discovered central limit theorem right here. You sum random variables, you get a normal distribution. What's the mean of this normal distribution? 5, right? What's the variance of this normal distribution? Or standard deviation? So, just to remind you, the variance of the demand in one city is a 12th. Because it was uniform 0, 1, variance of uniform 0, 1 is a 12th. So now, what is the variance? What should the variance of this normal be? I don't need Excel here, although we can check ourselves in a sec. 10 twelfths. The variance should be 10 twelfths because we summed 10 cities, right? So they sum 10 cities, they're independent, the variances add exactly like the means added. And if you want the standard deviation, it's square root of 10 twelfths. And what would I do, so you asked me what this centered average was. What if I wanted this distribution to be about 0? What would I do? I would subtract 5, right? If I subtract the mean, I would move this to 0. So I have this centered average column here. So let me ask you to do one more thing. And in the centered average column, I would like you to... Okay, so subtract 5. So I'm subtracting the mean. That's the centering. And I'm not exactly going to do the average. If I was doing exactly the average, I'd be dividing by 10. I'm going to divide by the square root of 10. And we'll talk in a little bit of why I'm dividing by square root of 10 and not 10. But can you go ahead and do that centered average and give me one more histogram plot? So I'm centering it by the mean. That's the 0.5 times 10. And instead of doing exactly the average, I'm doing square root of 10. And we'll talk in a sec why I'm doing square root of 10. Okay, so you're getting another histogram plot. And your second histogram plot should be looking something like that. So it's centered about 0. It's a normal distribution, and it's a standard normal distribution in particular. So one thing, so if you want something that gives you the standard normal, you can center, you want to divide by square root of n. This isn't actually exactly the standard normal because I would need to multiply by the variance, but it's centered around 0. So now let me say in slides, what exactly is this central limit theorem? So first of all, we've got these two histograms, one centered about 0, one centered about the mean. They both look normal. What we've just done is we've discovered law of large numbers and central limit theorem, which are arguably two of the most important results in probability. They also explain to you why normal distribution is so important. Because if you go with me that sums come up a lot, basically, anytime sums come up and you have a fair bit of independence in the distributions, you're dealing with a norm. And what exactly do these two things say? And this is also why this square root of n thing is coming in instead of n. So law of large numbers, you know. This says I'm summing 10 cities and I'm taking the average. That should give me the mean. That's law of large numbers. I'm summing demand in 10 different places. I'm taking the average. I'm getting the mean. And this is deterministic. This is not a distribution, right? So when n gets large, I expect to be very, very close to this. I basically expect it to be a point mass, and I expect it to be some constant. But we definitely know that these sample averages can fluctuate, because if you look at your column M or your column L, your column L, this is fluctuating. It's not always exactly the same. Right? So there's this question of like, well, how close is this to that? And so that's my CLT, okay? And so what is the CLT? We're summing in independent, identically distributed random variables. So for us in our exercise, it was demands in 10 different cities. These were the demands in my 10 different cities. And let me look at this random variable that is the sum divided by the square root. And I think I really want to subtract off an n mu there. So what's the mean? What's the variance? What's the distribution? The CLT is telling us why this histogram plot was a bell-shaped curve. So the CLT is telling us, if I sum these indifference demands, I subtract off the mean. Mu here is the mean. So mu is like the expected value of x1. It's 0.5 in your Excel sheet. That's centering it. And I divide by sigma square root of n. Sigma is your standard deviation, so it's square root of 1/12 in our example. That should be looking like a standard norm. Equivalently, it's telling me that if I just look at the distribution of the sum, it should be approximately normal. The mean should be the expected value of any one of these cities times the number I have. Same thing with the variance. And why this square root of n? So let me try to do just a little bit of algebra to show why that square root of n is coming up. And if this is helpful, please, I hope it's helpful. If it's not helpful, we'll see. So if I look at what I've written here, right, this is x1 plus x2 plus, so I'm summing over my indifferent cities. N is 10. I'm subtracting off the mean. So mu is 0.5, that's the mean of one of those cities. I'm dividing by the standard deviation of 1, which is square root of 12, times the square root of n. And let me just do algebra for just a minute. So a little bit of algebra, I could equivalently write this as okay, so what did I do here? I just grouped terms, and why is this interesting? This is basically your sample average. Whatever you're doing a sample average, that's the sample average. And that's your mean. And now these n's cancel, right? So if those n's cancel, I'm doing something like square root of n times x1 plus x2 plus xn divided by n minus mu. And I got a sigma sitting out there as a constant. Now, this guy, if I just look at this, what should be happening to that inside term? Do you think your sample average is approximating your mean? Yeah, right? To 0, yeah. If I look at that inside term just like this should be going to 0. We believe that that sample average is going straight to that point, and the more and more observations I take, the closer and closer that should be. That thing's got to be very close to 0. The square root of n is coming in because basically if I want a distribution, if I want to know how are these fluctuations around this happening, this is telling me that rate of convergence is square root of n. So the square root of n is coming in because that is going to 0, but if I blow it up, it gives me a true distribution, and that true distribution is normal. So that's why we are dividing by square root of n. If that helped, go that didn't help, remember the histogram plot pictures, and remember that when you divide by square root of n, you get that nice spread out bell-shaped curve. If you weren't dividing by square root of n, if you were just dividing by n, as that n got large, you would basically be getting some point mass right at 0 if it was centered, or your mean if it wasn't centered. So you wouldn't really be having a good distribution. Is that?
From what I understand is that the the bigger and bigger sample we get, the closer we'll get to the mean. And that
Correct.
makes sense to me, but I don't get the centered average. Like, why do I even care about that?
So the closer you'll get to the mean, but is there a distribution around the mean, and what is that distribution? So the question, when you say the closer you get to the mean, right? Suppose I want to ask, suppose your estimate is 1.5. Does that tell me that my true mean is 1.5, or might it be 1.4? So you agree with me, when you estimate your mean, you're never going to estimate that and think that is exactly my mean. So now I want to ask the question of, okay, you got 1.43. What I really want is, how close am I to 1.43? So if I want to ask a question like, how close am I to 1.43? Now I need to know what's the relevant distribution to use. And the relevant distribution to use to answer that question is normal. And that's what the CLT is telling you. And if any of you have seen confidence intervals, if you've heard confidence, if you calculate them, have you seen normal distribution coming up in confidence interval? That's exactly why it's coming up in confidence interval. Because ultimately, you're looking at that sample average, you're trying to say, well, how close is my point estimate? And what we've just seen is that if I want to preserve a distribution there, it needs to be a normal distribution. So what you have to trust me on is that square root of n is kind of the right thing. I'm not telling you that. But I think Mike's question is super important, which is, what is this? This guy we're all comfortable with, right? But we've all observed that when you take this observation fluctuates. Especially when I did 10 different cities, right? When I did 10 different cities, you looked at column L, you got a whole bunch of different thoughts. So now the question is does that make a distribution? Right? So if I'm getting stuff close to the mean, how close? And so CLT is telling me something about how close.
So this is like the same line of thinking as to why you diversify like a fund with at least like 30 stocks, because even though the variance for each one might be here or there, that
It's exactly the same line of thinking. Yes. And I thought maybe it's helpful to, let's just do one double check for ourselves too. So we can calculate the probability the demand, the total demand in these cities is less than 4 in 2 different ways. So first, I could look at let's do it from our Excel sheet first. Okay. Laptop. Sorry, that's not even the right one. There we go, okay. So when we did this sum, if I wanted to estimate the probability that I have a demand less than or equal to 4, I'm looking at my histogram, and the probability I have something less than or equal to between 2 and 2.5 is 1. The probability I have something between 2.5 and 3 is 7. Between 3 and 3.4 is 43. Between 3.5 and 4 is 91. So to estimate that probability, oh wait, you can't see that.
Yeah.
Okay, so I've apparently lost my laptop. looking at histograms, right, and you can look at your relative frequencies, and you can add up your relative frequencies to get an estimate of the probability the demand is less than or equal to 4. Or I guess equivalently, you could do a count if of whatever column you have your data in, and they less than or equal to 4, and we've got 1,000 observations, and you can get something back. And for my simulation, it's coming back at 0.142. Is that close to what is coming back for your guys's? Can you just check that with your Excel? Yeah? Okay, now I just told you that we have a normal distribution. And this gets to your question, Mike, which is why do I care about this normal distribution? I know this sample average is close to the mean. Well, what's another way to do this? Why did I have to do the Excel simulation? I know I'm summing stuff. What's the distribution of this total demand? I'm telling you that the distribution of this total demand is normal, right? And the mean of that normal is 5, and the variance of that normal is 10/12. So that suggests that another way to calculate this is to do norm.dist in Excel, and you're evaluating it to 0.4. We've got a mean of 5. We've got a standard deviation of the square root of 10 divided by 12. And we want the cumulative, so I'm doing a 1. And, okay, and so I didn't write this down, so can somebody tell me what are you getting if you do that? So that's pretty good. They're not exact, but they're pretty close. Okay? This one's going to fluctuate, it's an estimation. But why do I care about knowing this total distribution of demand? Well, I make calculations like this. So once I know that it's normally distributed, it's not just questions about the mean I can answer. I can ask questions about like, well, what's the probability if I stock enough products for 8 million people that I will be able to satisfy them, right? That I will have extra products versus less okay, I didn't say that. So if I know the distribution of demand, I can ask questions about if I'm doing capacity sizing and I want to think about how much do I need to manufacture to be 90% confident I can satisfy my demand. This is the type of thing I need, right? So this is telling me that my demand is normally distributed, so I can make those types of calculations. That help? And what is your takeaway here? I think your biggest takeaway in the slide is if you have a sum, you've got a normal distribution, and how do you remember what the mean and the variance should be? The mean should be, well, there's n things in your sum, so multiply it by the mean of one of the individual things. And the variance, well, there's n things in your sum, so multiply it by the variance of one of the individual things. Right? So this is your big takeaway, is this bullet point right here. You have a sum, you got normal distribution, the mean is n times the individual mean, the variance is n times the individual variance. Is that good?
In this case, we use the random variable, but if the demand is not random, then it wouldn't be a normal distribution.
If you know exactly what the demand is?
No, we don't know exactly, but it's not like random. It has some.
Oh yeah, thank you so much. I meant to say that. So what's the beauty of this? I didn't even have to know what the demand distribution was. So I told you the demand was uniform, but the beauty of this is I don't even have to know what it is. This works for any distribution. It's absolutely not specific to uniform. We did the calculation with uniform because it's something that's very clearly not normal. Very clearly does not have the bell-shaped curve, so I wanted to make the point that we started with something that was just a flat line, and we got a bell-shaped curve. So if it can happen there, it can happen anywhere. That's your constructive evidence. The theory is that actually that could be any distribution. Why is that important to you in real life? It means you don't have to estimate the demand distributions for all the cities separately. All you need is a sense of mean demand in each of the cities and the variance of demand in each of the cities. And you need a sense that it's about the same. You need a sense that the demand in each of these cities is approximately the same distribution. That's what I mean by independent and identically distributed. And you need a sense there's not a lot of correlation between them.
would assume that each city has the same exact thing.
Yes, so one of the things you need, so there's two main things you need. One is that the demand in each city has the same distribution or close to the same distribution. And if it has close to the same distribution, it should have the same mean and the same variance. Yeah, so you do need that.
This is the assumption of the model.
Hmm?
This is the assumption of the model, right?
Yes, yes. In order for this to work, for me to be able to say that the sum is normally distributed, that is, there are two key assumptions in the model. One is that the distribution can be anything, but it needs to be the same in each of these different places. And there can't be too much dependence between the two different places.
Can you go back to the slide where you showed us that the variance is 1 over 12 and how we got 1 over 12?
Oh, I didn't actually make that calculation, I just told you. When we first looked at the uniform distribution, we looked at a mean and variance for it. And so at this point, you can believe me, if you have a uniform distribution, it's mean, uniform 0, 1 is mean 0.5 and variance a 12. And if you want to do the calculation is, so we need x squared minus expected value of x squared, that's variance. This one we know is 0.5, so I know this is minus 0.5 squared. That one I need to calculate, so it's a uniform distribution, I want expected value, so I'm doing x squared times the PDF, which is just 1. So I'm integrating x squared, so this would give me x cubed over 3, it's between 1 and 0, so that is a third minus a half squared, which is, so that should be a 12, so that should be 4 over 12 minus a fourth, 3 over 12 equals a 12. So that was just, I said it from other class. The other thing you could do is you could look at the demand in one of your individual cities. My Excel isn't showing, so I can't switch to my laptop. But if you do the standard deviation in one of your individual cities, you're going to get square root of 12. Is that good?
Yep.
And we just use the square root of 10 over 12 just because there's 10 cities?
Yes.
Okay.
Yes. Yes.
And then from a practical standpoint, so we have these calculations and I know that I have a 40% of meeting the demand if it's this. I mean, if you're a business owner, do you just have to make a decision based on what you're comfortable with of, I want to be absolutely sure I hit 90% of the demand, or
So-
and that's like a personal decision?
Those of you that have taken operations, how many have taken like the basic operations class? You saw a news vendor model? And a lot of times you use normal distribution for your demand. Here's why. And you had an overage cost and your underage cost.
Okay.
And that is what gave you, do I want to hit 90% of the demand, do I want to hit 80%, do I want to hit 70%? It depends on the overage and underage cost. And for those of you that haven't seen the news vendor model, I'm basically saying to know if you want to provision for 80% of the demand or 90% of the demand or 70% of the demand, you're comparing how costly is it to you if you have over products, if you have products that nobody wants, versus how costly is it to you if a customer wants your product and you don't have it for them to buy. And if you've seen that, that makes sense. If it doesn't, just sort of intuitively, hopefully you can imagine there's a cost trade-off going on there. Okay, so I thought it was good. We've seen the CLT. Let's see another place that the CLT comes up. And this is actually, I posted the homework 3. So the homework 3, it turns out that I'm doing a stock price model. And let's see how CLT comes up and find it. So this is useful for your homework 3. That's what I'm trying to say. So let's say you're investing in an S&P 500 index fund. You have a long time horizon and you plan to keep your money in the fund for 10 years. And you'd like to estimate how much money you're going to have at the end of 10 years. And you decide to use only recent return data, let's say from 2000 onwards, to help you with this calculation. So we're hindered because, again, I can't show my Excel file because I don't know what happened. But if you look at the return data.xls posted, this is just exactly the return data that we looked at the beginning of class. And if I was only going to use the last 10, maybe I'm going to use a little bit more than 10 years. Let's say from 2000, so 15 years. And if I started with $1, oh, that's fine, we can do 10 years. So 10 years, so that would be from 2005, not 2000. Just up here that. So if this represents my return in each of those 10 years, it means if I start with $1, my ending value should be this. Agree? So this is, okay, I start with $1, this is after year 1, this is then after year 2, up the way up to after year 10. So I don't want to be able to understand, what is this? What's the likelihood that I'm going to lose money? What's the likelihood that my portfolio is going to grow to more than $3 or 3x, right? So here's a question for you. What can be said about the distribution of the logarithm of v? Knowing that we just did the central limit theorem,
Oh, it'll be normal.
it'll be normal. Okay, so how am I going to see the central limit theorem come up in finance? There's something called a log normal stock price model. Why is there the log normal stock price model? Well, we all agree on this statement, right? There's nothing controversial about that. If I take the natural log of v, that's the same thing as taking the natural log of 1 plus x1 times 1 plus x2, all the way out to 1 plus, oops, sorry. Oh, and now it's not in focus. There we go. And you may not have quite remembered, but there's the rule for when you take the log of a product, you add. So this would be the same thing as log of 1 plus x1 plus log of 1 plus x2 plus log of 1 plus x10. So nothing controversial about that. That's just purely the algebra of log. What about sums? What do I think of when I think of sums? Normal. Okay, so hey, this looks like maybe one not model for this stock price evolution is to think that all these individual terms are a sum, and they should tell me that the natural log of v is normally distributed. So this is suggesting that the distribution of the natural log of v is normally distributed. So that's actually called a log normal distribution, not surprisingly. So why do I care about that? Because, so what if I want to make a calculation that's the probability I end with less money than what I started? So I'm asking for, let's look at 2 here. So basically, if I end with less money than I started, that means that v, not LNV, but v needs to be less than or equal to itself, right? And I started with $1. So if I started with $1 and I'm looking for the probability that I'm less than $1, because that's less money than I get started, what's the natural log of 1? 0. So that means that the calculation I want to make is the probability that the natural log of v is less than or equal to 0. That would be equivalent to me ending with less money than I started. We've just decided ln of v is normal, but what are the parameters? So if I use the past 10 years of that data, what are the parameters there? So I know I want to do a norm dot dist, and I know I want a 0, and the next thing is the mean. So I'm going to try one more time to see if my laptop's going to come. Oh, look at that, great. Okay, so now my laptop's coming on. So what are the parameters? So first of all, we said we're looking at the natural log of v, and let's do 2,000, because I think it's kind of a nice change of century, change of millennia. So in column D, in column C you're just having your returns, but in column D I'm going to do the natural log of 1 plus column C, right? Because that's exactly what I'm doing over there. It's exactly what I'm doing on my dot cam here, right? This is x1 is the return, so column C is exactly what x1 is, because x1 is my return. So I want the natural log of 1 plus the return. So here in column D,
Question.
yeah,
I don't understand why we have 1 plus that, like
oh. Why do we have 1? Because if I start with $1, right? And I wanna know how much $1 grows to in 10 years. So at the end of the first year, $1 has grown to 1 plus X1, where X1 is my return at the end of the first year.
But the dollar didn't grow to that, sorry, I'm just like not getting that, like we purchase a share of a stock for $1,
Yep.
and then we get a return on this dollar, if the return's 20%, then we only get 20 cents, so we have a,
But you didn't
we lost
lose the
80
dollar.
cents. Oh, we still get that dollar back? I have a poor understanding of how stocks work.
So, if you buy a stock, right, and it's worth exactly $1, and it increases in value by 20%.
Got it. Then you have that dollar and 20.
Yes, yes.
Thank you.
Okay, so that's why we got the 1 pluses. And so, the reason there's the 1 pluses is because if I start with $1 in 10 years, this is how much it's grown, and I don't know what the return is gonna be in each of those years. Okay, and so I'm trying to estimate, and what we've noticed on the dot cam is that if I think of this as a sum of random variables, I'm summing the log of 1 plus X1. X1 is the return. Column C is like my X1. Column C is like my X1 because those are returns in the different years. So if I want to estimate the mean of the natural log of 1 plus X1, the first thing I'm going to do in column D is I'm doing, okay, so that's log of 1 plus the return. Okay. And we can discuss how far back we want to go. I decided let's go back to 2000, so I'm not using data that's too old, but that is definitely up for discussion in terms of fitting the model. So let's take an average now. So if I only go back to 2000, and I take the average of column D, that's 3.94%. And if I want the standard deviation, that is 19.25%. You guys agree with me on that? No, I see faces that are not.
Are you allowing us to earn interest on interest or gains on gains? So can we take the $1.20 earned in 2000 and put that towards the return in 2001, or are we just restarting at $1 every year?
No, I'm putting $1 in the investment, and 10 years later, I'm taking it out, and I'm not touching it until
So
then.
we're allowed to earn compound interest?
Yes, yes,
Oh, okay.
yes, but only, you're earning compound interest in exactly this way. I'm not compounding every year.
Okay.
So every year I'm doing a compounding, I'm not doing a continuous compounding, that's the word I was looking for. Okay, so this is specifically exactly what I'm saying the ending value of your portfolio is. Is you put in the first, you put in the $1, at the end of year 1, you've got 1 plus X1, whatever that return turns out to be. At the end of the second year, well, I have this there, that's where I started with at the beginning of the second year. At the end of the second year, I'm gonna multiply that by 1 plus X2. And then we're using properties of log to go to the fact that I've got this sum of logs. And if I'm saying that's normally distributed, I need to know what parameters to put in here. I need to know what is the expected value of this guy and what is the variance. Would you agree with that? I need to know the expected value and the variance of every term in that summation. Okay, so if I want the expected value and variance of every term in that summation, over here on my Excel spreadsheet in column D, I've got the logs. Here I'm taking the average and the standard deviation. And now what do I put in norm.dist? Well, it should be, I want the 0. And then I got 10 of these things, right? 10. I want the value of my portfolio in 10 years, so that's 10 things in my summation. So I've got 10 times the average I just saw, which was 3.94%. So that's like, this is 0.394. And then for the standard deviations, I've got the square root, I can't do this in, I've got the square root of 10 times 0.1, that's a percent. 10 times 19.25 squared. and then I want a 1. So let's do this to get my standard deviation. It's equals 10 times that guy squared gives me the variance, and so I need a square root. Okay, so I'm getting like 0.608. So this guy here is equal to 0.608. And now I can make that calculation. So I've got equals norm dot dist of 0.394 square root of 0.608, comma 1. Oops. And I've done something wrong. Oh, I forgot the x. So that was 0, comma. And so that's about 30%, 31% probability there.
Why is the mean 0.394?
Did I do that wrong? So let's see. So 3.94% is the average of D75 to D90
Okay, times 10.
times 10 because I got 10 years out. Yeah. So we can talk about this guy a little bit more, but I want to save a little bit of time at the end of class because I wanted to hand out a survey just to know how things were going. So if you feel like this last one went over a little bit quickly, I will start next class saying a little bit more about this log normal models for stock. The thing you're noticing is I've just given you an example in a completely different context where CLT is coming up again. And you can definitely see that return is probably for finance people an interesting thing to calculate. Okay, so what have we learned? The main thing you've learned today is this idea that when you take sums, you want to think normal distribution. Homework is posted, so that's more on your log normal stock price model. And now I'd just like to have a little sense of how the class is going. So if you could fill out for me a survey, just let me know what you think, let me know what you like, let me know what you don't like, let me know what you'd like to see more of, less of. If you notice, we're just a little bit behind the syllabus, so I'm going to update that in the next week, and I will go a little bit by what you guys tell me. Not exactly, but I will try to take things into account. Oh, great. Okay. So I can do two.
Thank you.
Thanks.
That's not you.